A central processing unit is the electronic circuitry within a computer that carries out the instructions of a computer program by performing the basic arithmetic, logical, control and input-output operations specified by the instructions. The term has been used in the computer industry at least since the early 1960s. Traditionally, the term CPU refers to a processor, more specifically to its processing unit and control unit, distinguishing these core elements of a computer from external components such as main memory and I/O circuitry. The form, design and implementation of CPUs have changed over the course of their history, but their fundamental operation remains almost unchanged. Principal components of a CPU include the arithmetic logic unit that performs arithmetic and logic operations, processor registers that supply operands to the ALU and store the results of ALU operations, and a control unit that fetches instructions from memory and executes them by directing the coordinated operations of the ALU, registers and other components. Most modern CPUs are microprocessors, meaning they're contained on a single integrated circuit chip. An IC that contains a CPU may also contain memory, peripheral interfaces, and other components of a computer. Such integrated devices are variously called microcontrollers or systems on a chip. Some computers employ a multi-core processor, which is a single chip containing two or more CPUs called cores. In that context, single chips are sometimes referred to as sockets. Array processors or vector processors have multiple processors that operate in parallel, with no unit considered central. History. Computers such as the ENIAC had to be physically rewired to perform different tasks, which caused these machines to be called fixed-program computers. Since the term CPU is generally defined as a device for software execution, the earliest devices that could rightly be called CPUs came with the advent of the stored program computer. The idea of a stored program computer was already present in the design of J. Preece per Eckert and John William Mauchly's ENIAC, but was initially omitted so that it could be finished sooner. On June 30, 1945, before ENIAC was made, mathematician John von Neumann distributed the paper entitled First Draft of a Report on the EDVAC. It was the outline of a stored program computer that would eventually be completed in August 1949. EDVAC was designed to perform a certain number of instructions of various types. Significantly, the programs written for EDVAC were to be stored in high-speed computer memory rather than specified by the physical wiring of the computer. This overcame a severe limitation of ENIAC, which was the considerable time and effort required to reconfigure the computer to perform a new task. With von Neumann's design, the program that EDVAC ran could be changed simply by changing the contents of the memory. EDVAC, however, was not the first stored program computer. The Manchester Small-Scale Experimental Machine, a small prototype stored program computer, ran its first program on the 21st of June 1948, and the Manchester Mark Chapter 1 ran its first program during the night of 16-17 June 1949. Early CPUs were custom designs used as part of a larger and sometimes distinctive computer. However, this method of designing custom CPUs for a particular application has largely given way to the development of multi-purpose processors produced in large quantities. This standardization began in the era of discrete transistor mainframes and mini-computers and has rapidly accelerated with the popularization of the integrated circuit. The IC has allowed increasingly complex CPUs to be designed and manufactured to tolerances on the order of nanometers. Both the miniaturization and standardization of CPUs have increased the presence of digital devices in modern life far beyond the limited application of dedicated computing machines. Modern microprocessors appear in electronic devices ranging from automobiles to cell phones, and sometimes even in toys. While von Neumann is most often credited with the design of the stored program computer because of his design of EDVAC, and the design became known as the von Neumann architecture, others before him, such as Konrad Zuse, had suggested and implemented similar ideas. The so-called Harvard architecture of the Harvard Mark I, which was completed before EDVAC, also utilized a stored program design using punched paper tape rather than electronic memory. The key difference between the von Neumann and Harvard architectures is that the latter separates the storage and treatment of CPU instructions and data, while the former uses the same memory space for both. Most modern CPUs are primarily von Neumann in design, but CPUs with the Harvard architecture are seen as well, especially in embedded applications. For instance, the Atmel AVR microcontrollers are Harvard architecture processors. Relays and vacuum tubes were commonly used as switching elements. A useful computer requires thousands or tens of thousands of switching devices. The overall speed of a system is dependent on the speed of the switches. Tube computers like EDVAC tended to average 8 hours between failures, whereas relay computers like the Harvard Mark I failed very rarely. In the end, tube-based CPUs became dominant because the significant speed advantages afforded generally outweighed the reliability problems. Most of these early synchronous CPUs ran at low clock rates compared to modern microelectronic designs. Clock signal frequencies ranging from 100 kHz to 4 MHz were very common at this time, limited largely by the speed of the switching devices they were built with. Transistor CPUs. The design complexity of CPUs increased as various technologies facilitated building smaller and more reliable electronic devices. The first such improvement came with the advent of the transistor. Transistorized CPUs during the 1950s and 1960s no longer had to be built out of bulky, unreliable, and fragile switching elements like vacuum tubes and relays. With this improvement, more complex and reliable CPUs were built onto one or several printed circuit boards containing discrete components. In 1964, IBM introduced its System 360 computer architecture that was used in a series of computers capable of running the same programs with different speed and performance. This was significant at a time when most electronic computers were incompatible with one another, even those made by the same manufacturer. To facilitate this improvement, IBM utilized the concept of a microprogram, which still sees widespread usage in modern CPUs. The System 360 architecture was so popular that it dominated the mainframe computer market for decades and left a legacy that is still continued by similar modern computers like the IBM Z series. In 1965, Digital Equipment Corporation introduced another influential computer aimed at the scientific and research markets, the PDP-8. Transistor-based computers had several distinct advantages over their predecessors. Aside from facilitating increased reliability and lower power consumption, transistors also allowed CPUs to operate at much higher speeds because of the short switching time of a transistor in comparison to a tube or relay. Thanks to both the increased reliability as well as the dramatically increased speed of the switching elements, CPU clock rates in the tens of megahertz were obtained during this period. Additionally, while discrete transistor and IC CPUs were in heavy usage, new high-performance designs like SIMD vector processors began to appear. These early experimental designs later gave rise to the era of specialized supercomputers like those made by Cray Inc. Small-scale integration CPUs. During this period, a method of manufacturing many interconnected transistors in a compact space was developed. The integrated circuit allowed a large number of transistors to be manufactured on a single semiconductor-based die, or chip. At first only very basic non-specialized digital circuits such as NOR gates were miniaturized into ICs. CPUs based upon these building block ICs are generally referred to as small-scale integration devices. SSI-ICs, such as the ones used in the Apollo guidance computer, usually contained up to a few score transistors. To build an entire CPU out of SSI-ICs required thousands of individual chips, but still consumed much less space and power than earlier discrete transistor designs. IBM System 370 follow-on to the System 360 used SSI ICs rather than solid logic technology discrete transistor modules. DEC's PDP-8, INKI-10 PDP-10 also switched from the individual transistors used by the PDP-8 and PDP-10 to SSI ICs. And their extremely popular PDP-11 line was originally built with SSI ICs but was eventually implemented with LSI components once these became practical. Large-scale integration CPUs. Lee Boisel published influential articles, including a 1967 manifesto, which described how to build the equivalent of a 32-bit mainframe computer from a relatively small number of large-scale integration circuits. At the time, the only way to build LSI chips, which are chips with 100 or more gates, was to build them using a MOS process. However, some companies continue to build processors out of bipolar chips because bipolar junction transistors were so much faster than MOS chips. For example, Datapoint built processors out of TTL chips until the early 1980s. People building high-speed computers wanted them to be fast. So in the 1970s they built the CPUs from small-scale integration and medium-scale integration 7400 series TTL gates. At the time, MOS ICs were so slow that they were considered useful only in a few niche applications that required low power. As the microelectronic technology advanced, an increasing number of transistors were placed on ICs, decreasing the quantity of individual ICs needed for a complete CPU. MSI and LSI ICs increased transistor counts to hundreds, and then thousands. By 1968, the number of ICs required to build a complete CPU had been reduced to 24 ICs of 8 different types, with each IC containing roughly 1,000 MOSFETs. In stark contrast with its SSI and MSI predecessors. The first LSI implementation of the PDP-11 contained a CPU composed of only 4 LSI integrated circuits. Microprocessors. In the 1970s, the fundamental inventions by Federico Faggin changed the design and implementation of CPUs forever. Since the introduction of the first commercially available microprocessor in 1970, and the first widely used microprocessor in 1974, this class of CPUs has almost completely overtaken all other central processing unit implementation methods. Mainframe and mini-computer manufacturers of the time launched proprietary IC development programs to upgrade their older computer architectures, and eventually produced instruction-set-compatible microprocessors that were backward-compatible with their older hardware and software. Several CPUs can be combined in a single processing chip. Previous generations of CPUs were implemented as discrete components and numerous small integrated circuits on one or more circuit boards. Microprocessors, on the other hand, are CPUs manufactured on a very small number of ICs, usually just one. The overall smaller CPU size, as a result of being implemented on a single die, means faster switching time because of physical factors like decreased gate parasitic capacitance. This has allowed synchronous microprocessors to have clock rates ranging from tens of megahertz to several gigahertz. Additionally, as the ability to construct exceedingly small transistors on an IC has increased, the complexity and number of transistors in a single CPU has increased many-fold. This widely observed trend is described by Moore's law, which has proven to be a fairly accurate predictor of the growth of CPU complexity. While the complexity, size, construction, and general form of CPUs have changed enormously since 1950, it is notable that the basic design and function has not changed much at all. Almost all common CPUs today can be very accurately described as von Neumann stored program machines. As the aforementioned Moore's law continues to hold true, concerns have arisen about the limits of integrated circuit transistor technology. Extreme miniaturization of electronic gates is causing the effects of phenomena like electromigration and sub-threshold leakage to become much more significant. These newer concerns are among the many factors causing researchers to investigate new methods of computing such as the quantum computer, as well as to expand the usage of parallelism and other methods that extend the usefulness of the classical von Neumann model. Operation. The fundamental operation of most CPUs, regardless of the physical form they take, is to execute a sequence of stored instructions that is called a program. The instructions to be executed are kept in some kind of computer memory. Nearly all CPUs follow the fetch, decode and execute steps in their operation, which are collectively known as the instruction cycle. After the execution of an instruction, the entire process repeats, with the next instruction cycle normally fetching the next in-sequence instruction because of the incremented value in the program counter. If a jump instruction was executed, the program counter will be modified to contain the address of the instruction that was jumped to, and program execution continues normally. In more complex CPUs, multiple instructions can be fetched, decoded, and executed simultaneously. This section describes what is generally referred to as the classic RISC pipeline, which is quite common among the simple CPUs used in many electronic devices. It largely ignores the important role of CPU cache, and therefore the access stage of the pipeline. Some instructions manipulate the program counter rather than producing result data directly. Such instructions are generally called jumps, and facilitate program behavior like loops, conditional program execution, and existence of functions. In some processes, some other instructions change the state of bits in a flags register. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. For example, in such processes of compare, instruction evaluates two values and sets or clears bits in the flags register to indicate which one is greater, or whether they are equal. One of these flags could then be used by a later jump instruction to determine program flow. Fetch. The first step, fetch, involves retrieving an instruction from program memory. The instruction's location in program memory is determined by a program counter, which stores a number that identifies the address of the next instruction to be fetched. After an instruction is fetched, the PC is incremented by the length of the instruction so that it will contain the address of the next instruction in the sequence. Often, the instruction to be fetched must be retrieved from relatively slow memory, causing the CPU to stall while waiting for the instruction to be returned. This issue is largely addressed in modern processes by caches and pipeline architectures. Decode. The instruction that the CPU fetches from memory determines what the CPU will do. In the decode step, performed by the circuitry known as the instruction decoder, the instruction is converted into signals that control other parts of the CPU. The way in which the instruction is interpreted is defined by the CPU's instruction set architecture. Often, one group of bits within the instruction, called the opcode, indicates which operation is to be performed, while the remaining fields usually provide supplemental information required for the operation, such as the operands. Those operands may be specified as a constant value, or as the location of a value that may be a processor register or a memory address, as determined by some addressing mode. In some CPU designs, the instruction decoder is implemented as a hardwired, unchangeable circuit. In others, a microprogram is used to translate instructions into sets of CPU configuration signals that are applied sequentially over multiple clock pulses. In some cases, the memory that stores the microprogram is rewritable, making it possible to change the way in which the CPU decodes instructions. Execute after the fetch and decode steps. The execute step is performed. Depending on the CPU architecture, this may consist of a single action or a sequence of actions. During each action, various parts of the CPU are electrically connected so they can perform all or part of the desired operation, and then the action is completed, typically in response to a clock pulse. Very often the results are written to an internal CPU register for quick access by subsequent instructions. In other cases, results may be written to slower, but less expensive and higher capacity main memory. For example, if an addition instruction is to be executed, the arithmetic logic unit inputs are connected to a pair of operand sources. The ALU is configured to perform an addition operation so that the sum of its operand inputs will appear at its output, and the ALU output is connected to storage that will receive the sum.